Today we're going to look at energy bar charts. This is something that is it's just a tool we can use to analyze systems and specifically how energy moves around in those systems. Now at this point you should have already read this article that I have up here. If you haven't, then I would encourage you to do so either right after this if you're listening live, or you can pause the video and read it if you're watching later. But we can use a energy bar chart as a way of showing how energy moves in a system. Now sometimes I'll refer to energy bar charts as LOL diagrams. Okay, you see that? You have one bar chart here that makes an L, you have the circle in the middle, and you have the second L. So sometimes I'll call them LOL diagrams. The first important thing we need to discuss is systems. Now we have done a reading over systems. We've not really discussed them yet. For now, there are two types of systems. There are what we call an open system and a closed system. The system is simply the objects that are going to either hold energy or share energy in some way. Now, you can define the system however you'd like. Any number of objects can be in your system, right? We could say the whole universe is our system. But it's not very useful sometimes, right? So in this example, they give you an example 1, a person pushes a box initially at rest across the floor, and there's friction. They made what we call a closed system. See how all the objects, the person, the earth, surface of the floor, and the box, they're all inside of this? That's what we call a closed system. A closed system means that the energy stays inside of this outline the entire time. No energy is going to leave this. At any point, while this person's pushing the box, the energy is either in the person, in the box, in the gravitational field, or in the surface, the floor. That's the only places energy can be. So this is what makes that a closed system. In this example here, you'll see an open system, right? It says example 2, a person pushes a box from 0 position up a ramp. So just going to push a box up a ramp. You can see this person, whoever made this, define the system as the person being outside the system. And of course we know that's where the energy originally comes from. Without that person, right, the box is never going to get up there, right? It's never going to go up the slope. That's not how it works. So in this system here, you'll notice the person's out and energy is going to go into the system. We call this an open system. So closed system is where energy stays inside. An open system is where energy goes into or out of those objects that are defined as the system. Now, what does that look like? What does it mean to have closed or open systems on a bar graph? Well, in a closed system, we're going to be using, right, so instead of going through the tedious calculations of calculating the exact number of energy units, we call a joule, Joule. I know it's funny because of joules, but that's what it's called. It's named after a British scientist. So what you have here is the number, like we could calculate the number of joules and figure that out, but it's kind of tedious. So instead, we're going to abstract a little bit. We are going to have blocks of energy. Just like in that energy story, we're really going to use blocks. So we have so many blocks of energy here. The number of blocks is arbitrary. It doesn't matter. What does matter is that the blocks stay the same. So in this scenario, we see that there are, it looks like 1, 2, 3, 4 blocks of energy at the beginning. It's all chemical. And later there were 2 blocks of kinetic and 2 blocks of internal. Now I'm not gonna talk about the types of energy yet. Again, we're gonna talk about that together in a minute. But what I want you to see is there's 4 blocks before and there are 4 blocks after. So if we have a closed system, the number of blocks always stays the same. When we do these problems, these practice problems that you have, I encourage you to do a closed system at first. We can do open systems later, but closed systems are easier because the number of blocks stays the same. In this scenario, that's not what happens, right? In the beginning, where's the energy? The person's going to push it up. It's in the person. And since the person was defined to not be part of the system, the energy is not in the system at the beginning. Notice this is a completely blank bar chart here. And later, there are 1, 2, 3, 4, 5 blocks of energy on this side. So the way we would describe that is 5 blocks of energy entered our system from outside. Now, we know that came from the person, but it doesn't really matter as far as the bar graph is concerned. And that's what this little middle circle is for. So if you have a closed system, you really don't have to put anything there at all. I like to put the number of blocks that stay the same inside, but it doesn't matter. But what we have is 1, 2, 3, 4, 5 blocks of energy, and then a little arrow showing it goes into the system. So the circle kind of represents our system, and energy can go into the system. And that's what we see here. Okay, so again, you can go back and look at these examples. They're good examples. Let's talk about a few examples for ourselves first. Okay, we have a scenario. So Julia is going to run a 5K. Create an LOL diagram or energy bar chart for the following points. A is right before she runs the race, and B is after she runs the race. Okay, so this is going to be A over here. I don't know, I don't have a great writing device here. I just have to use the mouse. And this is going to be B. That's the way it's pretty much always going to be. A is going to be one point, B is going to be the other. For now, we're just going to have A and B. You can add C, D, whatever you can add. You can have as many of these different points as you want. But A and B will be great for now. So what we must do when we approach one of these, first of all, we have to define the system. Like I said earlier, I'm going to assume this is a closed system. So I'm not going to go through the process of writing out all the parts of the system, but you could probably figure it out. Julia's got to be part of the system. The air's got to be part of the system. The ground's got to be a part of the system. Depending on whether it's a flat race or there's some incline, I assume there's inclines and declines. The earth will be part of the system too, because there might be some gravitational effects, right? I mean, if she has to run up the hill, if you've run up a hill, you know that it's harder than running on flat land. And if you run down a hill, it's a lot easier. You have to actually be careful not to go too fast. So the way I approach these is I would look at what are the types of energy. So we're going to make a closed system. The next question is, what are the types of energy we need in this scenario? What kinds of energy are going to be changing during this race? So I usually think about it, okay, what kind of energy does she have before, and what kind of energy is it after? Well, before, where's the energy? Most of the energy is in Julia, right? She's got to run the race. She's got to run around. So what kind of energy is that? Well, that would be chemical energy. ECH. Now, if you're not sure why that's chemical energy, I would encourage you to go back and look at those energy type notes. But when we talk about people and the energy we use, we eat food, we have chemical energy that's stored inside of us. And we can use that chemical energy to start moving, to turn into kinetic energy. So we're going to put the same types of energy on both sides. So I have ECH on the left and ECH on the right. Other kinds of energy that might be important. And I should have been more specific here, actually, now that I'm looking at it. I want this to be, when she's crossing the finish line. And I don't have time to write that out or the means to write that out. So when she runs the race. Maybe like when she's getting to the finish line or she's almost at the finish line. So the second part is supposed to be she's running. Well, if she's running, it's going to be kinetic energy. So I'm going to put EK, and again, I'll put it on both sides, EK. Any other kinds of energy you think of? Well, again, hopefully you're tracking with me here. One I would think is, right, she's probably going to get warm, right? When you start running around, you get hot. You start to sweat. So I'm going to put a thermal as well. ETH for thermal. ETH. I'm probably going to stop there. You could also include others, right? You could include some sound energy if you'd like, right? Because when she's moving around, there's probably going to be sound as she, her feet smack against the ground. There could be internal energy, right? That's actually be a big component, but I'm going to ignore that for now. That internal energy would be like the energy lost because of friction, that sort of thing. I'm just going to keep it to these three. Okay, so now we need to actually assign these amounts. And I've got these blocks here. This is not going to be easy as thought, but whatever. I got these blocks, and I'm going to move these blocks around. I made it several blocks here. I'm going to move these blocks around and put them in different places. Now, like I said before, the amount, the actual number of blocks does not matter. You can put however many blocks you want in chemical over here. just remember that you have to be consistent, right? So, like I have to be able to put blocks in these other categories. So there is actually a lower limit on how many blocks I can include here. But if you ever get in a situation, you can change it, and you'll understand what I mean as we do more. All right, I'm going to start with, I don't know, I'll just pick a number. Let's say 4 blocks of chemical. And again, this is kind of tedious. I'm sorry. This is easier if you're doing it on paper by far, which you can do, as I'll talk about in a minute. Now you got these really big blocks. I don't know why they're getting bigger, but it can't do anything about it now. These should all be the same, just to be clear. All right, but 4 blocks of chemical. I'm going to say this is before she runs a race. She doesn't have any kinetic, and she doesn't have any thermal. Now, this brings me to a very important point that I'm going to make several times because it's kind of a big deal. When we show A and B, what we're really trying to show is the change in chemical in the types of energy. That is to say, she certainly has thermal energy before the race begins, right? She has a body temperature, as long as she's healthy, of about 98.6 degrees, right? So she has some thermal energy. And ultimately, you could have some thermal blocks here if you want to. It's just that you don't have to have those thermal blocks yet because we're just trying to show the change. All right, I'm going to leave this here. So at the beginning of the race, she has 4 blocks of chemical, no kinetic because she's not moving yet. And again, no change in thermal. This is sort of my baseline of 0. Okay, let's look at the next part. When she's running the race, maybe it's like when she's near the finish line. Well, I'm going to put maybe 1 block, 2 blocks, maybe 3 blocks. Again, I know these are getting bigger. I'm sorry. Okay, again, it's kind of arbitrary. I know that I only have 4 to work with, right? So I can't put more than 4 total on this side since this is a closed system. So maybe I'll put 3 blocks in kinetic. And I'll have 1 block in thermal. This would be one of several correct answers you could have. So when I have 4 blocks here, I have to have 4 blocks on this side. What does this tell me? What am I looking for? I'm looking for, when I would grade these, I'm looking for 3 things. Number 1, do you have the right kinds of energy? You need to have chemical. You have to have kinetic. I could overlook thermal because maybe you say, well, maybe she's in really good shape and a 5K, is not that big of a deal for her. I could see that, right? Or maybe she doesn't run that hard. Or maybe she kind of walks during the 5K. Whatever. You have to have chemical and you have to have kinetic in this scenario. Number 2, conservation of energy. If this is a closed system, which is going to be, then there must be the same number of blocks on both sides. So if I have 4 blocks on the left, I need 4 total blocks on the right. I can't have more and I can't have less if it's a closed system, which we're going to be making. And that's what I'm looking for. I guess the other last thing is, did they move in the right direction, right? Chemical should be decreasing because she's running. Kinetic should be increasing. Thermal, if you have it, should increase as well. Now, the amount doesn't really matter. I could add 6 or 7 blocks over on this side, and then I would just add maybe some more to chemical or some more kinetic and more thermal. The other point, and this is the one I talked about earlier that I'm going to mention several times, is the chemical here, right? Notice I gave her 0 chemical over here. This does not mean she actually has no chemical energy, right? I mean, she can probably finish the race, right? She's probably going to finish the race. She probably can at least walk around or keep breathing. Her heart can keep beating. All those things indicate she still has chemical energy. But what this shows is that there is 0 relative to where it was before. So you could think about these 4 blocks being and representing the amount of chemical energy needed to get to the point like right before the finish line. And now they're spent up. They're used in different places. Let's quickly talk about this circle in the middle. You can leave it blank since this is a closed system. If you don't want to leave it blank, another option is you can just, and I actually do this usually, I just put 4 blocks, since we're talking about 4 blocks total, I just put 4 blocks inside of the circle. In other words, there are 4 blocks in the system. And they don't go out, they don't go in. It's a closed system. They stay inside the whole time. Okay, now obviously this year we're doing things digitally. So how can I translate this digitally? Well, what I can do is I'm going to open Google Sheets. You can open your own Google Sheet. Again, just go to your drive and start a new sheet or whatever. And all I need to do is just put in, we're going to make a bar graph. You have two options. You can make two individual bar graphs, or what I would prefer is just make one bar graph total. So for that last one, we had E, CH, E, kinetic, E, thermal. And I'm going to put the numbers I had here. I had 4, kinetic was 0, thermal was 0. And then all you're going to do is go to this side here and then just repeat the same thing. E, CH, E, K, E, TH. And we're going to put our new values, right? Chemical was 0. Kinetic I had 3, and thermal I had 1. So once you have this set up just like that, again, you just repeat the same thing twice. You just highlight everything, insert chart. Now, you can see it automatically made this bar graph here. You should click this use column A as headers so you get like a key here. But then there you go. This is your bar graph. This is point A. I can see it's all chemical, 4 blocks. Point B, I can see 3 blocks of kinetic, 1 block of thermal. So when you're working on these energy bar chart practice problems, you can do them in Google Sheets, and then all you would need to do is you can just copy the chart. I think you can literally just click on the chart and hit Control-C, and then you could go over to the practice. I don't have it pulled up right now, and then just paste that in. And it'll ask you if you want to link the spreadsheet. That's fine. That's fine. Just make sure you use a different sheet or a different page file whenever you do different problems. Okay. Does anyone have any question? I'm going to do one more example, but does anyone have a question about this example here? So again, you can either raise your hand if you're here, or you can turn on your mic and ask a question on Google Hangouts if you're there. Okay, assuming there's no questions, I'm going to go ahead and move on to the next problem, or the next problem I came up with. All right, Theodore's going to fly his drone and land on top of a roof. Create an LL diagram showing A, or an energy bar chart, showing A before the drone flies on the ground, and B after the drone lands on the roof. So once again, we're going to use a closed system, I'm going to assume. So if I was going to name everything that's in the system, I guess I would say Theodore, the controller, the drone, and the earth, and the roof. That would be all the components to make a closed system. Okay, what kinds of energy do we need here? Well, when I see this, immediately I see, okay, if the drone's going to land up on the roof, I know that there's going to be some gravitational energy here. Okay, so I'm going to put E sub G. Again, put it on both parts, E sub G. Okay, what else? Well, if I guess the way I would think about this is, if the drone's going to get on top of the roof, where's the energy for the drone right now? Well, you probably know it's electrical energy. It's powered by batteries. You have to charge them, that sort of thing. So again, you should know these symbols. If you don't, you need to go back and study. Electrical energy is E sub E minus sign. I think these are the two that you have to have. Other ones you could have. You could have internal, again, because it's going to be air resistance. You could have, and I think you can make a very good argument for light energy, right? Because the way that this controller works, this remote works, is it uses typically radio waves, which is a form of light. So again, that would be a great one to have. Again, I don't think it's necessary. I'm going to keep it simple for this one, but you could easily have that one. You could have maybe a little chemical because, Theodore's got to move his hands around, fingers around. But again, pretty small. I wouldn't worry about it too much. So let's say we're good with this right here. So once again, we need to come up with we need to come up with blocks of energy. So I'm going to try to make my block of energy here. There we go. At the beginning, is there gravitational energy? It's up for debate. I mean, again, it's all relative, so I would leave it as 0. But just to show my point that you don't have to, let's say we think of like 2 blocks of gravitational energy. Okay, electrical energy. There should be quite a bit of that because, again, this is before the drone flies and it's on the ground, right? And I'm saying you could have gravitational energy because maybe, I don't know, maybe you're on a hill, right? You're on the ground, but it's a hill and it's above somewhere. It doesn't matter, really, is what I'm trying to get at. Okay, electrical. I don't know. Let's put 4 blocks of electrical. Okay, so then part B, it's after the drone lands on the roof. Gravitational has increased, so I got to have more than 2. Again, it's arbitrary how many you have. You can have 8, you can have 6, you can have 4. I'm going to stick with 4, I think. Actually, what I'm going to do is I want to show all the electrical going into gravitational. So I'm actually going to put 6 there. There we go. So I got 6. I'm going to have 0 in electrical. So I have, if I want to fill in this circle here, how many blocks are there in my system? There are a total of 6 blocks of energy in the system. And again, this is a closed system. They all stay inside. All right. So there we go. This will be another great example. And again, there are many other answers. I could have had, 1 block here and 5 blocks in gravity. I could have had even 2 blocks in electrical and, 4 blocks in gravity, or even 3 blocks electrical, 3 blocks of gravity. What matters is the following. Number 1, do I have the correct types of energy? You have to have gravitational. You would have to have electric. You could have, you could have thermal, maybe, if you think the motor gets hot. You could have some internal from landing or from air resistance. You could have some kinetic from Theodore, but again, it shouldn't matter too much, right? Those are pretty secondary. They're not wrong to have. You just don't necessarily have to have them. These are the 2 that are important. And do they move in the right direction? Gravity should increase since it gets on the roof. Yep. Electrical should decrease since it's using electrical energy to get up to the rooftop anyways. Yep. So this work checks out. Now, a reminder on the energy bar charts practice that you have 2 options for how you want to submit these. You can do them electronically, so that's using the Google Sheets. That's perfectly fine. If you want to find some software, I think there's one called Google Draw where you could draw out an energy bar chart. You can do it like that. And then the last option is if you want to do it on paper, I think that's easiest kind of, but then you have to worry about attaching it. You can do it on paper, take a picture with a phone or your Chromebook, and then upload it to the the assignment. Right, that's an option. So again, as you work on this, those are your options. You have until next Tuesday for this assignment because, again, I want you to take your time on it. I want you to ask questions if you have them, and so I'll be available for questions obviously the rest of this week and at the very beginning of next week as well. All right, please let me know if you have any questions.